Hi everyone, we're gonna do a question on an inclined plane, and this is something you're going to see a lot this year in mechanics. And at the beginning it looks a little bit weird and perhaps a bit intimidating, but after you've done a few problems of these you'll see that they're always very similar. So once you've got the hang of them, they shouldn't worry you at all. I dare say they can even get a bit fun if you have a small geeky tendency. Here in question 3 they say there's a force W that acts vertically downwards on a particle at rest on a plane inclined at an angle theta to the horizontal. So there's a plane, and I'm going to do a big diagram. It's a bit too steep. There's a plane like that, and in the example that I'm going to do they say that theta is 30, so I'm gonna add the angle to here, 30 degrees, and it says to find the components of the weight along and perpendicular to the plane. So here's a particle, there it is, and it has a certain weight, and the weight always points downwards, and as we all know, weight is green. That's the weight. And what they're asking us here to do really is to, as it says in the question, find the components of W along and perpendicular to the plane. So what does that mean? It means perpendicular, so along the plane means parallel to the plane, right? So if that's the plane there in white, this one here, then along the plane is this line. That line is along the plane. So in a way they're first asking us to find if this is the real force that's working on the object, this is the real weight, then there's a component of that that's going to make it want to go down the slope, right? That's why when you're on a slope you go down. There's a part of your weight that acts along the slope, but it's not all of the weight that acts along the slope. For example, so a way of understanding that it's not all of it is if you were just free falling with your weight, you would go much quicker than if you were going down a ramp, right? Because it's some of the force is going along the ramp and some of the force is going into the floor, and that goes into the reaction the floor puts back into you, and so on. But the weight is split really into those two forces. One of them goes down parallel to the plane, and the other part of the weight is going into the floor, but the actual weight is in that direction. Or we can split them, the real force, in two components. As we always do, the components have to be chosen at right angles, and here they're not chosen to be along the x and the y like that, because here it's much more beneficial to do it when you're on a slope. It's much better to split the components in what goes parallel to the slope and what goes perpendicular to the slope, even though the actual weight is going that way. So you're probably thinking we're going to need some angles, and the angle that we're going to need is the one between the weight and the components that we're interested in, right? Like before we had this force that was real, and we were being asked for these two components, one here and one there, and we had that if this was F, this is theta, then this was always F cos theta because it was the adjacent side, and that was always the F sine theta because it was the opposite side, which corresponds to this. That's why it's the opposite. They're the same size, right? So here we're also going to need the angle that it makes with the two directions that we're interested in, and one of the directions that we're interested in is that one along the slope, and the other one is that we're being asked for is the perpendicular to the slope. So that's this one here. That's perpendicular to the slope, right? Here there's an angle of 90 degrees, and so these are the two directions that we want to find out. In other words, this is the real force, so I'm gonna draw it in a continuous line, because real forces deserve to be in a continuous line, ideally a little bit straighter. So that's a real force, and these are our two components. So let's make a triangle or a rectangle, however you want to think about it, using these three directions, given that you know that your real force is going to be your hypotenuse, right? It's always the biggest one. If we're going to chop a force in two components, then that force has to be the hypotenuse. So chopping this one up in two, one of them is going parallel to the slope. It's then this side of the triangle, and if we want to make a triangle between this part and that part, then we need to join these two lines, right? We can join them up, making sure that this is the hypotenuse. Then the right angle needs to be there, right? The right angle needs to be this one here. So hopefully that makes sense. This is a hypotenuse, and that's the right angle that we've made in order to create a triangle here. Okay? And similarly, if you complete the rectangle, then this is really the triangle that we've made. This is a hypotenuse, and this is the direction down along the slope, which is the same as this one here. They're parallel. And then this one here in red is the same as this one here. They're both the same. So actually I'm going to paint this one in red so that you see that they are the same direction and therefore the same component of the force, right? Two forces which have the same angle and the same magnitude, they are the same equivalent forces. So here this force and that force are the same, and that force and that force are the same, and these are really components, right? They're not actual forces. The only actual force is this one vertically down, which is the weight. So that looks like a bit of a mess, and how are we going to find out an angle in here if we only have this angle here? And this I'm going to draw in big because it's quite important that you see it, but the conclusion is quite easy. You can even remember it if you want, but it's good to see why it's true. So I'm going to enlarge the diagram. Let's see, we've got slope, and we have the direction of the yellow vector, which is going down the slope, which I'm just going to put on top of the white so that we don't confuse the thing, because they're in the same direction. So you've got this direction, then you have the horizontal, which is the one that marks this angle here, 30, and then there is the red line coming like that, right? So that's really what we have. We have the yellow going down the slope, the red perpendicular, so this is perpendicular here, and then we have this horizontal there. And then finally we've got our weight, and the weight is the one that chops this angle here, and so I'm going to take that right angle off so that we can see it for clarity. This is the weight direction, and we want to know this angle here, because that angle is what will give us well, let me complete the yellow side also here, because I haven't done that. This rectangle, if we completed the direction of the force that is going down the slope, is parallel to this one here. Right, this one and that one are parallel, and this is our rectangle of forces, and that's our triangle. So we can look at this line here, the red one, as the one perpendicular to the slope. So if this is W, then the red line is going to be linked to W by this angle here, whatever that angle is. We call that theta, right? Let's call that theta. Then the force that is going perpendicular to the slope into the slope here, and this is perpendicular, will be W, which is the hypotenuse here, all of that, times the cos of that angle, because this is the adjacent, so that will be W cos theta. And this one down here, which is opposite to the angle, will be sine, and it's going down the slope, so that's the other one that they're asking us, which is going to be W sine theta. And now we need to know what theta is. So theta in terms of this 30 here, well, let's see. That's 30. If this is 30 here, then let's have a look at this large triangle. Simplifying it a little bit, we have this, and then we have that, and then we have that. Simplifying it, this is 90 degrees, so I'm taking this large one here, right, from here to there, ignoring the weight one. So here we have a right angle, this is 30, and so if this is 90, and then these two have to add up to 90 because triangle has 180 degrees inside of it, so then this has to be 90 minus 30, right? So let's call this angle generally, instead of 30, let's call it alpha. Then let's call that angle alpha. Then if this is alpha, then this is 90 degrees, and this is 90 minus alpha. Then that means that this angle down here, that one, is 90 minus alpha, right? Or 90 minus 30. Then since this one is 90 here, then you've got that one is going to be 90 minus this one, right? Because that's 90 and these two are 90. So the one that we're interested in here, theta has to be 90 minus this one here. And this one here we just said was 90 minus alpha. So in other words, we can say that theta, which is the one that we're interested in there, is equal to 90 minus this one, and this one is 90 minus alpha, so we can say theta is equal to 90 minus alpha. And so 90 minus 90 goes to 0, and minus alpha goes to plus alpha. So theta is equal to alpha. So in other words, this all sounds very complicated, but all you need to know then at the end, if you understand it, that's even better, but you need to know that this angle here, 30, whatever that is, theta, is always going to be equal to that one there. So these two angles are the same. So in other words, here the answer to this question you could just write, and once you do a lot of practice with these, you can write them straight away, and it's very easy. You can say that the component of the weight down the slope is just going to be W sine W sine 30, because that there will also be 30, and the sine of 30 is this guy here, which is the opposite, so that's the one that goes down this way. It's the same as this one here, and that's the opposite of the angle. Hopefully that makes sense. And this is parallel to the slope. And you can always remember that if you want that the weight times the sine of the angle is the one that goes down the slope, and the 1 times cos of the angle is the one that goes into the ground. So if there's a particle here, like here, then down that way will be W sine 30, that's what is pushing it that way, and in and into the slope would be W cos 30. Okay, and that would always be the case if the angle is 30. If the angle is something else, then that angle goes there. So this would be useful, for example, if you wanted to calculate how much it accelerates when it's going down the slope, then you know that the force accelerating it, given if there's no friction, this would be the force. So that would be your resultant down the slope. You would take your force resultant to be W sine 30, and that would be equal to mass times acceleration. And from there you can get your acceleration divided by the mass. And so just to summarize and to make it not seem too hard, whenever you have something on a slope like that, and this is the angle theta, and this is the weight W, then the amount of the weight that goes in that direction will always be W sine theta, and the amount of weight that goes into the slope will be W cos theta. This is also useful, and it will be useful when we do especially things to do with friction, because friction is a product, it's a function of how much you're pushing into the floor. Hopefully that makes sense, right? The more you push into the floor, the more the friction is likely to get involved in the problem. Alright, hopefully that helps, and see you in the next video.